Again, last time, what did we do? We started talking about integration by parts. So let me remind you. So recall integration by parts. And the formula is that if you integrate something of the form u dv, this integrates as u times v minus the integral of v du. Okay? So what this suggests is that when you're doing integration by part, typically it's going to look like a product, the stuff inside your integral. It doesn't have to be. Remember that sometimes you can take dv to be dx, for example. So 1 times dx. So in that product, you need to pick who is u and who is dv. And you need to make a smart choice. Typically, whatever you pick for dv has to be something that you know how to integrate. Okay? For example, let me start with a warm-up. So let's see the integral, and this time let's do the definite version because we didn't do any definite integral last time. So the integral from 0 to pi over 2 of x cosine of x dx. Okay, so as you can see, here is a product, and as we saw last time, when you have a polynomial, this has the form polynomial times a trigonometric function times cosine or sine. This case is cosine. When you have this shape, you want to use integration by parts, and I already gave you a hint. I gave you a suggestion of what should be your choice for u and your choice for dv. Let's see, who remembers? What should be our choice for u here?
X.
Very good. So here we want to let x be u. Okay, so the polynomial is what we make for u, and then the rest will be our dv. Everybody okay with this? So u equals x, and then dv equals cosine of x dx. Now we find the remaining two things that we need. We need du and we need v. Okay, so we take derivative. Du is just dx. And then to find v, remember we do this by integrating our dv. That's how you find v. You just integrate whatever your dv is. So what's the integral of cosine? The integral of cosine is positive sine. Be careful, Daniel. Is sine of x. Now here, in general, it's plus c, but we're just looking for an antiderivative, just one antiderivative. Okay, so we don't have to write the plus c. Are we okay with this? All right, so now we use the formula. So the formula says that this equals to u times v. So u times v, so that's x times sine of x. Now this is a definite integral, so you have to evaluate. Okay, minus the integral, you put your limits, of v du. So that would be sine of x dx. Questions on this first step? Okay, and now we proceed as usual. Okay, so over here, I'm going to go ahead and evaluate this first part. So that's going to be pi over 2 times sine of pi over 2 minus 0, because 0 times sine of 0, that's just 0. Then minus, and now let's integrate the second integral. So the integral of sine, that's negative cosine, right? So this is going to be a plus. I'm going to put cosine of x, and then evaluate from 0 to pi over 2. Okay? So we have, remember that sine of pi over 2, what sine of pi over 2? What is this? It's equal to 1. Good. So that's equal to 1. So here we just get pi over 2 plus, and then here we have cosine of pi over 2 minus cosine of 0. What's cosine of pi over 2? 0. What's cosine of 0? 1. Very good. So we get as an answer pi over 2 minus 1. Questions? Any questions? Again, this is just a warm-up. We did problems like this before, last time. It's just that we didn't do it with limits of integration. So I'm showing you how it looks like if we had limits of integration. So Daniel, I gave you, so if I think I didn't see you last time in class, but remember, if if you are not in class, you should look at the notes. Otherwise, you're missing important stuff. Okay, and remember that I also record the lectures. Okay, so last time when we talk about this, we talk about this type of integrals. So let's see. Let me show you specifically where we are. For example, we did this one, number 4, x squared times sine of 3x. We did it. Oh, that's a short. Oh, I think I didn't write it down. I said it out loud, but I didn't write it down. Well, let me show you here. For example, we did this example of a polynomial times an exponential, and then I told you every time that you have an integral like this, you always want to let your polynomial to be your u and the exponential to be your dv. And the reason for this is because, you know, the idea is that when you use integration by parts, you want to make your integral simpler, okay? So this same thing that happened to the exponential, you do it for sine and cosine. If you have polynomial times sine or polynomial times cosine, your u is always a polynomial and your dv is the other function. Now for logarithm, it's the other way around. If you have a polynomial times a logarithm, it's the other way. Your u is your logarithm and your dv is a polynomial, okay? Now, if you want the reason why we say that this is the best thing to do is because the idea is that when you use integration by part, you are changing this integral for this one, really, okay? Your integral is not going away. You're just changing one integral for another one. The hope is that this second integral, this other integral that you get is easier to do than the previous one, okay? So let's take a look at this. Here, there are two choices really. U is either x or cosine, okay? Let's see. If I would have picked u to be cosine, that's not going to change the situation too much because du would be sine. So cosine and sine is pretty much the same thing. Okay. Now the problem is that if I let dv be equal to x dx, now my v would be x squared. Okay, x squared over 2. So when you put your formula and you integrate v du, you're going to be integrating x squared over 2 times the sine function, or negative sine in this case. The point is that integral is more complicated than the original one because now sine and cosine, it doesn't matter, but instead of x, you have an x squared. So you see that the degree went up, and that's not good. You're complicating the problem. Now, on the other hand, if we let u be equal to x, that's good because when you take derivative, remember when you take derivative of a polynomial, you make it simpler. You drop the degree by 1, at least, okay? So if you take the derivative, now the x is gone, and it just becomes dx. And so we know that the second integral that we get is pretty simple, like as you can see, it's a sine of x. If that would have been an x squared, we do the same thing. It's just that the integral then would be 2x times sine of x. But that's simpler because instead of x squared, now we need to deal with x sine of x. You do by parts again, and you're done. By letting u equals x, etc., etc. Do you understand why? So that's the point that, you know, in the case of polynomials, taking derivative, it makes it easier because it drops the degree, okay? The only exception is when you have a logarithm, that in that case, your logarithm should be your u, and then the du, the dv will be the polynomial. All right, so let's see. Let me now show you all the situations in which integration by parts is useful, but the problems are a little bit more interesting. And you may not be used to solving integrals this way, but you know, they show up. So for example, what do we do if we have a product of sine and exponential? And the same thing that I'm going to do here is if you had a product of a cosine with an exponential, okay? It's the same technique. Just going to do the example with this one. So I like to call this type of integrals equation-like integrals. And you're going to see why I'm calling this an equation-like integrals in a second, okay? So since I already know what's going to happen beforehand, I'm going to go ahead. I'm going to give it a name to this integral, okay? I'm going to call this integral, I'm going to call it I for now. Okay, I'm just gonna call it I and I for inter. Okay, so let's go ahead and let's solve this. So first of all, this is a product, right? And always before even trying by parts, you should think and see if you can make any substitution, any reasonable substitution that will make your job easier. Okay. Here it doesn't seem that any substitution will really help us too much, so we don't have to worry about that. So let's go ahead and let's try by parts because we see a product. Now here we need to decide whether what should be our U and what should be our dV. That's always the question. What's U, what's dV? Now, there is really no particular choice here because, when you integrate an exponential, you get exponential. When you take derivative of an exponential, you get the exponential. So it doesn't really matter what you do with the exponential, integrate or derivative. It's just a constant, the difference. But constants are not a problem. Just take them out, and that's it. And sine, the same thing. When you take derivative of sine, you get cosine. When you integrate sine, you also get cosine. So again, it doesn't really make a difference. Do you understand what I'm saying? So here, exponential and the sine function, they both have the same level of complexity here. So it doesn't really matter. You cannot go wrong with your choice. Here, your U can be whatever you want, and then, of course, the V is the other guy. Do you understand this? Okay, so when you see this situation, just take your pick. Now, here is something important. You need to be consistent because you see what's going to happen now. Because basically, we're going to change this integral for another one that would be exponential with a cosine, right? When we do the steps. Now, you have to be consistent. If you decided that your U was exponential, we need to keep making U our exponential, okay? You cannot decide to then later change because if you change, everything will cancel out and you're going to get 0 equals 0. And then you didn't do anything. Okay, so you just need to be consistent with your work. Just keep that in mind. Okay, let's see. I will let you decide. What do you want? What do you want to pick for you? Do you want the exponential or the sine function? Okay, so let's pick u to be the exponential. So u is gonna be equal to e to the 3x. So dv then is sine of 2x dx. All right, so now we find the u. That would be 3 times e to the 3x. Remember, chain rule, okay? And then v, that's going to be, what is this? Negative cosine of 2x divided by 2. Yes? Everybody following what's going on? Okay, so now let's use our formula. uv, so e to the 3x times negative cosine of 2x over 2 minus v du. So v negative cosine of 2x over 2 times 3 e to the 3x dx. Oops, wait, I forgot the dx here. Okay, so let me clean this up and make this look a little bit nicer. So let's see. Now this is going to be, I'm going to put a negative 1/2 here, e to a 3x cosine of 2x. Now here the minus comes out, making this a plus, and then a 3/2 comes out, and then we have the integral of e to a 3x times cosine of 2x dx. So as promised, all we really did was we changed our integral for this one, and they're basically the same level of complexity. They're essentially the same type of integral. Do you understand this? It doesn't get worse. It didn't get worse, but it didn't get better either. I mean, we are at the same spot, basically, that we were before. Do you understand what I'm saying? Okay, good. Now, what's the idea? This type of integral, they will exhibit a property that's called, it's a cyclic behavior. Now, what I'm going to do is, I'm going to take this integral, and I'm going to do by parts again. And what's going to happen is that now when I do by parts here, the original integral is going to return. Okay? And then we're going to solve this as if it was an equation. You will see what I mean in a second. So the point now is that we're going to do by parts again. So remember what I told you. we need to be consistent. So because we pick u to be e to the 3x the first time, we need to keep doing this for the second time. Okay? You cannot change it now. You are free to make your choice at the beginning, but once you make a choice, you need to stick with it. Then the u is gonna be 3 e to the 3x dx. And v, so what's the integral of cosine of 2x? Integral of cosine of 2x? Good. Sine of 2x over 2. Perfect. Okay, so now we go at it again. Okay, so wait, we need to write here negative 1/2 e to the 3x cosine of 2x plus 3/2. Now be careful. You need to open up a bracket, right? Because we need to put our formula or integral inside that bracket because the 3/2 is multiplying the whole thing, okay? So uv, so as 1/2 e to the 3x sine of 2x minus the integral of v du. Now, if you don't mind, I'm going to go ahead and put the 3/2 outside that I get already. And then we have e to the 3x times sine of 2x dx. Okay, questions? Are you okay up to here? All right. So notice that what happened is, well, we actually came back to where we started because now the integral that we have is the original one. So the integral that we obtain here is the same as the original one. Well, what do? Yes, it may look like we're going in circles, but not really. We can actually take advantage of this to solve it. So remember that I decided to do this I. So let me write the problem to hopefully make it easier to understand for you. So what we really have is that our integral, that we call it I, equals negative 1/2 e to the 3x times cosine of 2x plus, I'm going to distribute the 3/2, okay? Plus 3/4 e to the 3x times sine of 2x minus 9 over 4 I. Do you understand this? All I did was I rewrote the problem, but instead of the integral, I put I. Are we okay? Yes or no? All right. So now let's see. Here is a question for you. What is our Oh, sorry. I muted myself with this headset. Okay, anyways, can you hear me now? Okay, so I was asking, okay, a question for you. What is it that we need to do now? So what is it that we're looking for? What are we interested in knowing? Very good. We want to know the value of I, right? Because I is our integral. So there you go. Here you have a little equation and you solve for I. And this is actually linear in I because the other stuff doesn't have an I in it. So this right here stays there. We don't touch it because then there is no I. All you have to do is take this guy, bring it here, collect like terms, and solve for I. And done. It's like having this equation. I equals whatever you want minus 9 over 4i. And I ask you solve for I. And let's say, let me just put something simple here. Now you ask me a question. Give me a second. Hold on. Let me just put something here, like, I don't know, 3, whatever. and I ask you, let's say 3x, and I ask you, solve for I. It's exactly the same thing that you need to do here. Move it to the other side, combine like terms, and then divide by the coefficient. Okay? All right, so let me address your questions before we continue. So, Melanie. So why we have minus in 1/2? Okay, well, that was at the very beginning. Are you talking about this minus, this one? Is this the one that you're talking about? Okay, that came from here, okay? That's this minus that we have from the very beginning. Okay, I saw somebody else raise their hand, but then you guys lowered it. No problem. Any other questions? I think somebody else had a question, but lower the hand before I could spot the name. Well, okay, if you have questions, then you ask. Okay, anyways, now you know what to do, right? So the idea now is that we solve for I. So now, solve for I. So I'm gonna add I. So 9/4I plus I is gonna be equal to this. Combine on the left. So what is this? 4/4, 9 plus 4, that's 13. So you get 13/4I equals this. It will 3x times sine of 2x. And then finally, multiply by 4/13. Like multiply by 4 and then divide by 13. So times this. And now remember that we are calculating an integral. So what do we need to write at the end of our integral? What do we write at the end of the answer? Plus c. Very good. Don't forget that. Okay. So moral of the story. Integral of e to the 3x times sine of 2x dx. That was original, right? Equals. Okay, let's see. We can do something nice here. I'm gonna pull out the e to the 3x, and I could bring in the 4. And here's what I'm gonna do. I'm gonna pull out the e to the 3x common factor, and I'm going to factor in, I'm gonna distribute in the 4. You okay? What I'm about to do? Just to get a nice expression. Okay, so we're gonna have e to the 3x over 13, that's gonna stay outside, times, and now I'm gonna put the positive term first. When I factor in the 4, it cancels the 4 of the 3/4, and we get 3 sine of 2x. And then when I factor in the 4 in the first term, that's a minus, it cancels with the 2, but then I get a 2 on top. Minus 2 cosine of 2x. And this looks nicer than the original one. Looks cleaner. Okay, questions? Could I go back? Go back where? More than this? Okay, guys, remember that these notes are available for you. You don't have to worry about taking pictures and so on. Do you know how to access the notes? But Melanie, do you know how to access the note? Because this concerns me, because if you have to study later, then I want you to be able to see the stuff that we do, in case that you cannot find your own notes or whatever. Do you want me to show you how to get the notes? And all the notes are posted. So Jason, I'm sharing this notebook. So everything that I've written for you in the class is there for you to see. Okay. Yeah, the classes are recorded, but I understand maybe you don't want to watch the recording because you know it's too long, blah blah blah. But you can always go to the notes, and you go and you see the notes, and you can see everything. I mean, I don't mind showing you what we have done at the beginning. I'm just telling you, so don't stress that you don't have to. If you fall behind writing or whatever, don't worry about it. You can look at it later. Okay? It's better if you pay attention and you try to follow the thought process. This is what I really feel is more helpful for you to be able to follow along and understand what we're doing. It's always good to write yourself stuff so you really understand it. But okay, anyways, this is one of the things that I guess is sort of new from today, which is this type of intervals that exhibit this cyclic behavior, meaning that when you are solving the integral, the same integral pops up in the process. Now, this is the technique. If this happens to you, just solve it like an equation. Just call it I or whatever is your favorite letter. Just don't use the same variable that you have. Like don't use X, for example, in here. Just call it whatever letter you want and then solve it like an equation, and there you go. Okay, so that's a, I guess, slightly new idea. Are we okay? Let me do another one, for example, with an inverse trigonometric function. So how we do x squared times arctangent of x. Let's integrate this. Okay, so we don't know what's the integral of arctangent. What we know is what's the derivative of arctangent, but we don't know the integral. Therefore, you should not pick dv to be arctangent. So here, even though you may want to let u be x squared, that's not a good choice because then we need to integrate arctangent. Yes, again. Okay, can you hear me now? I don't know. I just stop moving. I move too much, and then I press stuff that I should not be pressing. Okay, okay. So back online. Well, I was online. My voice is back. Anyways, what I was saying is, did you catch what I was saying about the choice of U and DB or no? Okay, good. So here we should let U be arctangent, okay? Because we don't know how to integrate arctangent anyways, or not in an easy function, okay? It's just like the ln situation. We didn't know how to easily integrate ln, so we didn't make it our dv. We pick it as U, okay? Same idea. So when you have polynomial times an inverse trig function, could be arctangent, arcsine, whatever, this is the technique. U should be the inverse trig function, and then dv, the polynomial, okay? All right, so let's go. So then du, remember you need to know this. What's the derivative of arctangent? Very good. So 1 over 1 plus x squared dx. And then what is v? X or x cubed over 3. All right. So is everybody else okay? Because I feel like the same students are the ones that are always answering the questions. Just want to make sure that everybody is following what we're doing. If anybody has a concern, please speak up. Okay? Don't stay quiet. All right. So now we do uv. So that will be 1 over 3 x cubed arctangent minus the integral of v du. So v du. That's okay. I'm gonna pull out the 1 over 3, and then we get x cubed on top, and then 1 plus x squared. All right. So now what we need to do is we need to be able to solve this rational integral. This is not too fun unless, because we will talk about rational integrals later. In general, you do them using another technique. And let me see if I can see something that we can do now easily. Mhm. Okay, so I'll tell you, the standard technique here is to do division. Okay? Shouldn't be a -1. Where is the -1? We have a negative there. Jason, what do you mean by a -1 when you take out the 1/3? You are always allowed to take out constants from an integral. You don't have to, there is no -1. Remember, the -1 is when you change limits of integration. If you flip the limits of integration, then you put a minus in front of the integral. But here, all I'm doing is I'm taking a constant out of the integral. You can always do that without changing anything. Okay. All right, good. Okay, so I'll tell you, the standard technique to use here is to actually do long division. So when you have something like this, an integral of a rational function that is improper, the degree of the top is greater than or equal than the bottom, what we do is we do long division, okay? And you're gonna learn this in a few sections down the road, pretty soon. But right now here, we can also do another trick. If you don't want to use the division trick, I mean, we're big guys, we know how to divide, so let's do it. But we could also use a substitution, okay? We could let u be 1 plus x squared, then du is gonna be 2x dx. We have an x in there, and then the other x squared that remains will be u minus 1. And then we can get away with that. So let's see, do you want to see it with the substitution or do you want to see it with the long division? How do you want to see it? I would say that with the long division is cleaner, and you will learn this later anyways. So it's good that you start seeing a preview of that. But take a pick. What do you want, long division or substitution? Long division. And Melanie is being greedy. She wants to see both. Okay. So, okay. Let's make your wish come true. So first, let's do it with long division. So long division. So basically we divide. So remember, when you divide two things, you always write in the form of quotient plus remainder over divisor. Okay? So we go ahead and divide x cubed. We divide it by 1 plus x squared. So I should write this as x squared plus 1. Then we put an x in here. And this is going to be x cubed plus x. Then we subtract. These guys cancel. Then we get negative x. So we stop because the degree here is less than x squared, right? The degree is 1 and our divisor has degree 2. So we stop. So what this means, so what you get from here is that x cubed over 1 plus x squared can be written as follows. So quotient plus remainder over divisor. That's what it means to divide, okay? It's just a way of writing your expression in this form. Did you understand this? So, and you can easily check. So basically that means that this expression equals x minus x over x squared plus 1. If you subtract these two, you're gonna get x cubed over 1 plus x squared. Okay? Did you understand the long division? Now, why is this helpful? Because now I replace that fraction for this one, and we know how to integrate this. The first one is an easy integral. The second one is a little u sub, right? So let's do it. So we get the integral of x squared inverse tangent is going to be 1 over 3 x cubed inverse tangent minus 1 over 3 times, and then I'm just going to replace, instead of x cubed over 1 plus x squared, I'm going to write this. Okay. Now, okay, so okay, and I'm gonna do that one with the little you saw. So the first one is easy, right? So integral of x is x squared over 2. I'm gonna distribute the negative 1 over 3. Let me just leave it like this. So integral of x is x squared over 2 minus, now I'm gonna integrate the other one. So for the other one, I'm gonna make a substitution, okay? So I'm gonna let u be 1 plus x squared. So du is 2x dx. So that means x dx is du over 2. So that integral becomes the integral of 1 over u du over 2. Are we okay? I'm talking about this one over here, this integral. That's the one that I'm analyzing now, okay? Are you okay? Okay, I hope yes. Otherwise, I waste too much time waiting for you to say yes or no. And then the time goes by. All right, so just stop me. If you have a question, please just raise your hand and stop me. Okay, that way I don't have to waste time asking you. So minus x squared over 6, then plus, I'm distributing the negative 1 over 3. I'm going to pull out the 1 half, so it's going to give me a 1 over 6. That's 1 over 3 times 1 half. And the integral of 1 over u, that's ln of absolute value of u. And always remember plus c. Now I'm going to put u back, but because u is 1 plus x squared, that's always positive, so I don't really need the absolute value. Okay? So minus x squared over 6. Let me write it as 1 over 6 x squared. It looks nicer. Plus 1 over 6 ln of x squared plus 1. All right? Questions?
I have a quick question
Yes.
that's related to this and the test. So, like, when we're supposed to show our work on the test, so like here in this previous step, you did ln absolute value of 2. So, like, if we did this problem on our paper and in the picture we sent you, we did like ln parentheses u, or just ln u without any parentheses or absolute values, would that be counted against us, or does that not matter? As long as we end in the correct form.
If you end in the correct form, that's fine. The stuff before is just your way of getting to the answer, right? So as
Right.
long as you understand what you're doing, is if I see that you put the absolute value at the end, if it has to be an absolute value, like for example, if it would have been 1 minus x squared, let's say, you have to put absolute value,
Right.
okay? Because that could be positive, that could be negative. So you need an absolute value there.
Okay.
Here you don't because it's always positive. Also, you put the absolute value. You can always put it. You can never go wrong with putting the absolute value.
Right.
So
Okay.
it's just that if you realize that it's positive, it's nicer to say I don't need it, and then you don't write.
Okay.
Okay. Okay. Can you hear me now? Okay. There's something strange. All right. So what I'm saying, remember that I told you that there could have been two ways to solve this, and I said long division is kind of the way to go, but we could have done it with substitution if we wanted to. That integral x cubed Okay, so you know what? I'm gonna do something else. Okay, I'm gonna do something else, guys. I'm gonna use the microphone from my tablet instead of the microphone from my computer. And hopefully that's gonna work better. Let's see. Okay, can you hear me? Okay, so let's do this. Okay. Okay, here we go. So again, let's use substitution now. Okay. So the idea is that I'm gonna let u be 1 plus x squared, then du is gonna be 2x dx, as mentioned before. So x dx is du over 2. That's not a problem. So let's go to our integral and let's see what we can do with this. All right, so remember, this is really substitution. So our job is just to replace whatever we have in our integral. We want to get rid of all the x's and we want everything to be u, okay? Now, the x cubed, we can think of it as being x squared times x, okay? And so we can already see that the 1 plus u plus the 1 plus x squared, we have a substitution for it, right? That's our u. Now the x dx, we have a substitution for it. That is du over 2. All we have left is we need to figure out what to do with this fella. What do we do with x squared? Well, we can come here and say, well, if u is equal to 1 plus x squared, it follows that x squared equals u minus 1. Okay? So then I write here u minus 1. Did you understand this? Okay, perfect. So let's see, this is 1/2. I'm gonna put the 1/2 out. And now to integrate this, we can easily break up this as two fractions. So we're gonna get 1 minus 1 over u. Okay? And now we integrate. So that will be 1/2 u minus 1/2 ln, absolute value of u. And then we put back what this is. So 1 plus x squared minus 1/2 ln of 1 plus x squared. Now, let me see. Okay, here we go. So this is what we obtain if we decided to use this. Do you understand this? Okay, now you may be wondering, hold on a second, this is not exactly the same thing as what we got originally. First of all, we have 1 over 6 over there, but that's okay. The 1 over 6 is because of this 1 over 3. Remember that we had a negative 1 over 3 distributing over our integral, okay? So that negative 1 over 3 is going to change the sign and it's going to make this guy positive and this one negative as expected, right? And also it will put a 6 in the denominator. So that's not a problem, right? The really concern is this term versus this term over here. Because you see the ln part is the same. That's not a problem. And we already addressed the coefficient. It's the negative 1 over 3 that's being distributed. Now here we have an x squared and over here we have a 1 plus x squared. What's going on here? Can anybody enlighten me here? What do you think is happening? This is typical when you are solving integrals. This kind of stuff shows up. And sometimes you think that your answer is different than somebody else's, and they're actually equivalent. You just need to realize what's going on. If you're not used to this, let me show you quickly. I'm gonna do one more line. I'm gonna go ahead and I'm gonna distribute this 1/2. Okay, which remember, very good, Adam. But let's make it more clear so everybody can see it. I'm gonna distribute the 1/2, which remember it really would be a negative 1 over 6 because of the negative 1/3 that we had originally. Okay, but the question is, how do we get rid of that constant? That's really the question. So we have this. And then now notice that I have my term here with the x squared by itself, just like the original answer that we obtained. But then what do we do with this 1/2 that is floating around by itself? Well, we have 1/2 over here, and we have an arbitrary constant over here. So an arbitrary constant plus 1/2 is just another constant. So what we do is we put it together, and we call that nu c. So this is just 1/2 x squared minus 1/2 ln of 1 plus x squared, and then plus c, where by c here is just, an arbitrary, a new constant. If you want, you can call this one c1, and then this one is just c. If you want, we can call this one c1, and then c is c1 plus 1/2. But it doesn't matter. C1 is arbitrary, so c is also arbitrary. Do you understand? No, Melanie, the inverse tangent, that's from before. Remember, the discussion is when we arrive here, the focus was on this integral, and then we said, and then I told you there are two ways to do it. We could do it by using long division, or we could do it from the beginning using a u sub. And then I was planning, first we did it with long division, and then one of you wanted, I think you wanted to see actually the other version. So that's why I explained here the other version, but just that integral, because the other part is the same. It comes attached to it, right? Okay. All right, good. Okay, very good. That was nice. So let's see, what do I want to do now? Let me do this problem before our time runs out. So let's do a volume problem, okay? Let's do a volume problem. This way we practice more volume. So okay, and then find the volume. Of the solid obtained by rotating the following region. So the region given by y equals sine of x, y equals 0, x equals 2 pi, x equals 3 pi. So that's the region, and we're going to rotate this about the y-axis. Okay, that's the question. So we want to find the volume of the solid obtained by rotating this region. Let's see. Let's see if you can tell me more or less what type of solid we're going to obtain. Let's first draw the picture. This is a typical example. So we have the sine function. Everybody knows how the sine function looks like, right? Now notice that the sine function, the main period is from 0 to 2 pi, but this time we're interested between 2 pi and 3 pi. So we need to draw two periods of the sine function. So remember, it goes from -1 to 1. Let's say that here is 2 pi, and then over here we have pi. Split this in 4 pieces, and then 4 pieces again. So this is pi over 2, 3 pi over 2, and then this is 3 pi here in the middle, and then this is the same thing as saying 4 pi over 2, so 5 pi over 2. And just for completeness, let's do this one. That's 6 pi over 2, and then 7 pi over 2. Okay, so sine function begins down here at 0, then up here at 1, down at 0, then -1, back to 0, and then continue the same thing. 1, 0, -1, 0. Okay, let me sketch. I'm gonna do this part like this because we don't really care about from 0 to 2 pi. Now begins here what we care about. This is the piece that we really care about. And on the sine function keeps going to the right, keeps going to the left, etc. But what we care about really is the piece that I did in solid. We okay with this so far? All right, and then the y-axis, the y equals 0, so that's the x-axis, and then from 2 pi to 3 pi. So that means that we're talking about this region right here. That's the region, and this one is the function y equals sine of x, and we want to rotate about the y-axis. Okay, so let's see, how do we do this? What's the first thing that we need to do? We need to place a rectangle, right? How do you want to place a rectangle? Who can tell me? What's the smart choice? Very good, vertically. If you put it horizontally, if you put a horizontal rectangle here, it's not gonna be easy. First of all, you need to solve for x, meaning you're gonna have an inverse sign, and then that will be in your radius formula. You will have to use Watchers, and then you will need to square it, and you will need to do the integral of inverse sine square, so to speak, and that'll be pretty complicated. I'm not even sure if you'll be able to. It's something that can be computed easily. Okay, so it's not a good idea to put it horizontally. So vertically is the way to go. Very good. It's pretty easy to figure out what the height of the rectangle is by making it vertically anyways. And that's the idea. As long as you can control your height or length of the rectangle, that's all you care about. Okay, one way or the other. Okay, good. So now that we place a rectangle, then we can already write several things. First of all, we already can say what's the method that's going to be used. What's the method? Shells. Very good. Good. Second, we can say the variable. What's the variable that's going to be used? The variable is x. Very good. And remember, because it's shells, that means that we already have a formula. So the volume will be the integral. Let's see, from where to where? What are my limits of integration? From 2 pi to 3 pi. And the formula is 2 pi r of x, h of x, dx. Okay, everybody okay so far? So remember, you need to know that shells, it comes with this formula. Okay, you need to know the formulas for the different volumes, the different methods. Okay, so now let's go back to the picture because our job is to figure out what is R and what is H. So let's see, in the picture, R, remember, is the distance between your rectangle and the axis of rotation. So this right here is R of X. Okay, that's R. And then H, in this case, is the height of the rectangle. All right? Okay, so let's see. What's the formula for H? Who can tell me the formula for H? The sine function. Very good. H is just given by sine. And how about for R? What is R? R is going to be X. Very good. Yes, very good. Very good. X tells you R. You don't have to add anything specific. So R is just X. So Jason, if you do, well, if you do, I guess, should be x minus 2 pi, probably what you're thinking, because 2 pi minus x, notice that x is bigger than 2 pi. So that would be a negative number. But if you put x minus 2 pi, you are just talking about this little piece here. This little piece is x minus 2 pi. But that's not what you want. You want the whole thing. You want all the way down to the y-axis. Does that make sense? So it probably would have been more interesting if I would have said to rotate about the line x equal 2 pi. So let me just, I mean, we're not going to do it like that, but let me just put it here for a second. If I would have said to rotate about this line, x equals 2 pi, what would be, so h is still sine of x, okay? What would be r in this case? because now r is just this piece right here. So what will be the formula? No, be careful, Jason. So x minus 2 pi, very good. Notice that x is bigger than 2 pi. X is between 2 pi and 3 pi. X is this position right here. This position here is x. So remember, you do right minus left. So x minus 2 pi. That would be this little distance here. Okay? But all right, I said y-axis, so let's stick with the y-axis. Unless you want me to change it. I think it's nicer if we change it. That way, I mean, the integral will be more interesting. Y-axis is fine. Okay. You guys don't like it when I say it's nicer. All right, so what happened there? I raised too much. Oh, we're gonna leave it like that. Okay, so and then in this case it's just x. Okay. No, what I'm saying is that if we put the line x equals 2 pi, that would be harder than the y-axis. The y-axis is easier. Because, you know, first of all, it's just x, and therefore your integral is more friendly. Around the y-axis is easier, because how does the integral look like? It would be 2 pi x times sine of x. If I would have said x equals 2 pi, the axis of rotation, first of all, it's more complicated to figure out what r was, because you have to think more. You need to realize that is x minus 2 pi. So what will change is that here we will have an x minus 2 pi. That would be the difference. If I would have said that the axis was x equals 2 pi, the axis of rotation, then instead of an x, we will have this term here. And then we need to integrate that. That's all. Okay? All right. So, but let's stick with this. And now, you know, we do it. And the point is that to do this, what technique do we need to use now to do this integral? Integration by parts, because we have polynomial and a sine function. Now, do you all remember the shortcut that I mentioned yesterday? Let's take advantage of the shortcut. And if you don't remember, then I'm going to remind you again. Here we have x times sine of x. I pull out the 2 pi, okay? So I'm going to put x here. I'm going to put sine of x here, and then take derivative. And here I take integral. Integral of sine. What's the integral of sine? Negative cosine. And the integral of negative cosine, that's negative sine. So we do this and this. If you don't like this, that's fine. I don't like it either, but it's faster. So I like it when I want to save time, and now I want to save time. But if you don't like it, you can use the long process. And in fact, try doing the problem with the original version, the original approach with the formula, integration by parts, and make sure that you get the same answer, okay? Then this is positive and this is negative. So the antiderivative is negative x times cosine, and then will be minus sine, but then there is a minus that makes it plus sine of x. And plug in your limits of integration. Okay, so we have negative 3 pi cosine of 3 pi plus sine of 3 pi, and then minus negative 2 pi cosine of 2 pi plus sine of 2 pi. All right, so let's simplify this. So cosine of 3 pi, what's cosine of 3 pi? That's the same thing as cosine of pi. Remember, cosine has period 2 pi. So the same thing as cosine of pi, and cosine of pi is negative 1. Sine of 3 pi, that's 0. Sine is 0 and multiples of pi. Cosine of 2 pi, that's equal to 1. Sine of 2 pi, that's equal to 0. So this is 2 pi times, let's see, what do we have here? Negative 3 pi times negative 1, that's positive 3 pi. And then minus 2 pi, that's plus 2 pi. So 5 times 2, so we get 10 pi. Nice answer. Okay. Questions? Any questions? Okay, sounds good. So remember, try doing this same integral by using integration by parts and make sure that, verify that you get the same thing. Okay. All right. We have 5 minutes left. I wanted to show you. Okay, what's going on now? Tell me.
So earlier when we did integration by parts on, it was problem 2, the integral of e to the 3x times sine 2x.
Yes.
Right, you said when we do it by parts, and we need to take it multiple times, always have u be the same thing. So did you mean
Yes.
always have u, like if we start with u equals e to the 3x, u can
You have
only
to stick
equals
with
e
it.
to the 3x, or u
Yes.
has to be an exponential?
No. And at the beginning, you have a choice.
Right,
You decide what you want.
right.
But once you make your choice, you need to stick with it
Okay,
throughout the problem.
so it has to be the same exact thing throughout the entire problem, not just the same kind
Yeah.
of function.
And well, the same kind, because for example, in the same way that we say you could have said dv. We put dv to be sine, but then in the second one, our dv is a cosine. So the same type. In the case of u, it just turns out that e to the x is so nice that when exponential are nice, so that when you take derivative, it becomes the same thing, right?
So
But
like,
for example, you could have set u be equal to sine. That's fine.
mhm,
It's just that then the second integral, your u must be the cosine. Okay.
okay, all right.
So
So it,
just be consistent with that.
okay, so you just have to keep it the same kind of function. It doesn't necessarily have to be equal to each other.
Yeah, no, because if they are not exactly the same, then
Right.
how does that make, right?
Okay,
Okay,
got it.
all right, good. So let's see. I was gonna do secant cube for you, but secant cube we're gonna deal with that anyways in the next section when we do trigonometric integral. So I don't want to uh, bring noise, but let me get this integral out of the way because you will need this for the next section. I don't know if this shows up in the homework, and if it does, I don't want you to suffer because of this. So here is an integral that you need to know, and my advice to you is just memorize the result. Okay, don't just memorize the result that we're about to obtain, because if you want to reason through it every single time, it's going to be a pain. And this integral will pop up a lot for you, so you need to know what it is. Okay, so let's see, Melanie, y is plus 3 pi. Okay, so there's a negative here, right? And cosine of 3 pi is -1, so negative times negative is positive. You see it? Okay, good. Okay, so integral of secant. How do we do this? Well, basically, it's just a trick. Okay, all right, no problem. So basically, it's just a trick. So to do the integral of secant, what we do is the following. I'm gonna go ahead and multiply top and bottom by secant plus tangent. And why am I doing that? You may wonder. Well, you're gonna see in a second why. So I'm gonna multiply top and bottom by secant plus tangent. And in this case, the numerator becomes, what's the numerator here? This is secant squared plus secant tangent. Okay, now let's do the following. I'm going to make a substitution. Let u be secant plus tangent. What's the derivative of that? What's the u? What's the derivative of secant? Derivative of secant. secant tangent. And what's the derivative of tangent? Derivative of tangent, Adam? Secant squared. Good. So now take a peek at the numerator. What do we have in the numerator? That's exactly the derivative, right? So what happens when you're doing an integral and the numerator is exactly the derivative of the bottom? What's the answer for this integral? Should I go with the substitution, or do you know exactly what's going to happen? What happens when you have an integral? So here's my question to you. Let's say that you have this integral. What's the answer? When the top is the derivative of the bottom. Can you tell me? ln. Very good. This is ln of absolute value of the function. Okay? Because you measure u sub, then u is f, and du is the top. So that's the integral of 1 over u, which is ln of u, and then you put your f back. Moral of the story: the integral of secant is ln of the absolute value. This is important, the absolute value, secant plus tan. Okay? So make sure that you know this. You need to know this because this integral is going to pop up in many situations, and you don't want to be playing that trick every single time. You just want to remember this result. Okay? So the integral secant is ln of absolute value of secant plus tan. And you can do a similar thing to figure out the integral of cosecant. So we don't have time, but I'm going to leave this to you as a homework. Now that you know what's the integral of secant, so homework, see if you can find the integral of secant cube. Because secant squared is easy. Secant squared is just tangent, right? The integral of secant squared is just tangent. But how about secant cube? Hint, write it as secant times secant squared and use by parts. Okay? In this case, use by parts, and notice that the easier one to integrate here is secant squared. So use by parts by making u be secant and your dv secant squared. And see where it leads you.